All right, so let's pick up where we left off last time. So we are here.
Which slide is that?
It says slide 18 or 24.
Okay.
All right, so we have been really working on the sequence of these gradients, and I've been drawing the pulse sequence diagrams to kind of really help lock that in. And the timing of the gradients for this chapter is the most important thing. Not so much drawing the actual pulse sequence, because we'll cover that a little bit more when we actually cover spin echo pulse sequences, and then next semester we're going to cover gradient echo pulse sequences. But you can see how the timing also applies to our pulse sequence diagram, because you have to show when the gradients are actually applied on each line. And you can see that the slice select gradient is turned on first when we are delivering that RF excitation pulse to excite those hydrogen protons, flip them into the transverse plane. Then our phase encoding gradient is switched on next to create a phase shift of those hydrogen protons. And that changes every TR. So as you start to fill K-space, each row of K-space is filled every TR. So TR1, one row of K-space. TR2, the second row of K-space. And it goes on until you've filled every single line of K-space. That's why TR is incorporated into our scan time equation. And then finally, we need to collect the signal, so our frequency encoding gradient is turned on last. What is another name for our frequency encoding gradient?
Readout.
Good, readout gradient. So you can see here as the signal starts to regrow because of our 180-degree refocusing pulse, we sample the signal. And right at the middle, where we have peak amplitude, is what? Our time. Which time, though? Our echo time. Exactly. So our TE is always going to occur before our TR, because our TR is from our 90 to our next 90-degree RF pulse. So know the timing of these gradients. So slice select first, phase second, frequency encoding third. All right, so we basically have all this data that we've encoded on all three axes. So we need to put this in K-space, which is where we store all this signal. So all these raw data points are stored into K-space. Is K-space the actual image? No, remember, it still has to go through that mathematical process called the fast Fourier transformer that occurs in the array processor. And basically all the high amplitude areas from K-space are going to be your bright areas on your MRI image. So it is a grid of a sort, but you don't actually associate certain areas of K-space with the same areas on your image. So high amplitude areas usually result in bright pixels on your MRI image. Low amplitude areas of K-space usually result in the darker areas on your actual MR image. So let's review K-space, because this is kind of one of the more important concepts you need to learn for the registry and for the second half of the test this weekend. So K-space usually has, it's a square or a grid, and the frequency axis is going to be your horizontal axis or your x-axis down here. Your phase axis is going to be the vertical axis or your y-axis. Frequency is usually encoded on the long or short anatomy axis.
Frequency long.
Frequency long, most of the time. Phase is going to be your shorter axis of the anatomy. K-space is determined by polarity, because your phase shift could be positive or negative. So the top half of K-space is going to be positive, and the bottom half of K-space is going to be negative. Usually it gets numbered from the middle axis here out. So imagine we have a matrix of 128 by 128. What does that mean? How many rows are we going to have? What do you think? 128. And then how many data points are we going to have on the frequency axis? 128. Yeah, so that gives you your grid. Your matrix will give you your grid. So let's put that over here. So imagine we have a 128 by 128. And if you ever see a matrix that are not equivalent on both sides, usually the shorter or smaller number is going to be your phase encoding axis. So if it was 128 by 64, 64 is typically going to be the amount of rows you have. Because once again, you want the shorter or smaller axis of the anatomy to be in the phase direction, because that's associated with your scan time equation. So it usually gets numbered in this way, where the central axis acts as 0. It's your baseline. And then we said the top half of K-space is positive. So you would actually get a positive 1 for your first line above your central axis. And then right below it, you would get a negative 1. So that's where it starts. Those are going to be usually your shallow phase encoding gradients, where we have very little phase shift. And then it goes out to, so what do you think this number would be? Negative what?
64.
Good. Negative 64, because you have to divide 128 by 2. So the bottom would be negative 64, and then the top would be positive 64. Okay? So that's usually how they number K-space. So your rows start from the middle and they go out. And that is associated with your phase shift. So, what do you think fills the middle of K-space when in terms of your phase encoding gradient? A steep or a shallow phase gradient? What do you think? A shallow. So the middle of K-space is associated with a more shallow phase encoding gradient. And to fill the outer portions of K-space, you have to select a steep phase encoding gradient. Okay. There are different ways you can fill K-space. We'll talk about that when we do our review. There's spiral. You can do Cartesian, which is just your normal top to bottom or bottom to top. You can do central K-space filling, where you actually are more concerned with filling the middle of K-space, which is associated with the signal and contrast compared to the resolution. There's keyhole filling. There's partial or half Fourier filling. So we'll talk about all the different ways we can fill K-space. And a lot of these were created to save time, because our MR images usually take a long time to acquire. So a lot of times we have to have the patient hold their breath. So we need to fill these lines of K-space very rapidly. So we create a lot of half Fourier techniques, partial filling, things like that to really speed this process up. The unit for K-space is radians per centimeter. Radians are basically just the unit of degrees in a circle. So remember, our phase, if you think about it in that watch analogy, if you're starting at 12 o'clock, if you have a small phase shift, say you're only going to 1 o'clock. But if you have a large phase shift, your spins have gone out of phase and they're starting to get more and more incoherent, and say you're at 9 o'clock. So a small phase shift is associated with a shallow gradient. A large phase shift is associated with a steep gradient. So that's why the signal that's usually put into this row has pretty low amplitude, because there's a lot of phase shift, there's a lot of decay going on there. But when we fill the middle of K-space, it's very high amplitude signal. So we have very high peaks of our frequency curves. So we get a lot of signal that is associated with the middle of K-space. But just remember the units for K-space are radians per centimeter. K in K-space means frequency. So make sure you know that. So K is associated with frequency. So it basically means frequency space. Alright, so these are the most important things you need to remember about K-space. There's several facts that apply every time you fill K-space. These are always going to be true. Number one, K-space is not the image. This is where we're storing the raw data that still needs to go through the fast Fourier transformer, which occurs in the array processor, to create the image. That fast Fourier transformer is a mathematical process that basically assigns a certain shade of color per pixel.
So, is K-space just happening when you're like waiting for the image to show up when you're scanning MRI? You know how like it comes right up with X-ray and CT. So like in MRI, it's not. We had to wait a little bit for the image. So is that K-space? Like is that?
I mean, it's slowly happening. Yes. So you're encoding the signal, and it's basically filling K-space as you're scanning. And then once, say, an entire block of K-space is filled, that creates one slice of your image. So sometimes in MRI, you can put that little live box up, and it shows you one slice as they are acquired. So it takes like 20 to 30 seconds for an actual slice to show up, and that 20 to 30 seconds is the time where we're filling K-space.
Okay.
Correct. But usually you have to wait a little bit longer for it to go through that mathematical process, which doesn't take very long, it could be milliseconds for that to occur. But then an image shows up. But that's just one slice of the pulse sequence. And then you acquire another slice, and then another slice. And so once you have all the slices acquired, you'll have your complete pulse sequence. But good, yeah. Okay, so rule number one, K-space is not the image. It's just basically where we're storing all that signal. Number two, data are symmetrical in K-space. It's called conjugated symmetry. So the top is equivalent to the bottom. And that's because of just our polarity. So we apply our phase encoding gradient if we have a shallow slope that's associated with the central rows of K-space. We also have to apply it in the negative fashion, but we're going to have the same slope of that phase encoding gradient, just in the negative polarity. And then same with the steep gradients. If we have a positive steep gradient, we also have to have a negative steep gradient. So very symmetrical. So the exact same amount of phase shift, but just in the opposite direction. It's also symmetrical right to left. And we know this is true because that is going to be basically our sampling window. So remember, our sampling window is basically the time that our readout gradient is on. So remember, I gave you the example where I said our readout gradient sampling time is 8 milliseconds in total. It's usually divided into two parts. What are those two parts?
Rephase.
Good. Perfect. Rephase and dephase. So our signal needs to regrow. And rephase equals how many milliseconds? 4. Because you just divide it in half. And then dephase. So once again, very symmetrical. So you can see here how the signal's regrowing to peak amplitude. And then this right here is your TE, right in the middle. And then it starts to dephase again. So the signal and those data points are very symmetrical on the left side of K-space as opposed to the right side of K-space. So you can see here how we've used this to our advantage. So if we fill the the top of K-space, we basically know all the data points are going to be very symmetrical for the bottom. So what they do is just do half Fourier fill, where they'll fill the top, or they'll basically acquire the signal for the top half of K-space, and then they'll do what we call zero fill, and they'll basically fill the bottom of K-space with a bunch of zeros, and interpolate the data, and it'll basically half your scan time. So there's great ways to reduce our scan time. All right. This third point, the center portion of K-space contains data that has high signal and low resolution. So see here how our amplitudes are a lot higher in the center? So that gives us a high signal. So I would say all this area right here, this gives us high SNR and contrast to noise ratio. Okay? Because we can see the amplitudes of that signal and those data points are a lot higher. We get more signal from that. So those are going to be your bright areas on your MR image. And then everything out in the periphery is going to be associated with low signal but high resolution. So all the areas outside of this circle that I just drew on here are basically going to give you your resolution. So everything else is resolution. So in MRI, if you had to choose one, signal is way more important than resolution. You want to get at least some signal back, and resolution is a luxury. So imagine if you're imaging, doing an angiography exam, MRA, and you have to image very rapidly to catch that bolus going into the abdominal aorta, where you have to basically start your scan right as that bolus hits the abdominal aorta. We're going to be more concerned with the central portions of K-space. We'll fill those areas first to get high signal from the abdominal aorta. And then if we have time, we'll fill in the periphery of K-space to get better our resolution. But we'd rather see that bright contrast in that vessel compared to making out, the small structures. Fact number 5, scan time is associated with how long it takes to fill K-space. Scan time equation. Can somebody give me a scan time equation? Good. And PE can also be written as number of phase encodings times X. Okay, in a traditional spin echo pulse sequence, each row is associated with 1 TR. So each row is associated with 1 TR. So you can see here, if we have 128 phase encoding steps, we have to do that 128 times. So that gives us basically the two first variables within that equation. Our TR is from 90 to peak echo, or 90 to 90? 90 to 90. Number of PEs are basically your rows in K-space. And then next is, if I fill this row once with signal, that's just going to give me 1 next. But if I go back and fill it again at the same phase encoding gradient step, it's going to double the amount of signal going into that row. And what it does is averages that signal within that row, but it increases our signal, which is a good thing. Sometimes we really need to increase the amount of signal, especially if we have a very high resolution image, which is good, like in MSK. Sometimes if you have very small pixels, it's hard to get good signal within that pixel, so we have to boost up our next. So if we increase this next to 2, we basically have to go and fill every row of K-space again twice. So our scan time is going to be doubled. Okay? The dimensions of the case, last important fact, the dimension of the K-space determine pixel size. So we can see here how we get the rows from our phase encoding steps by applying different gradient strengths in the phase direction. But it's also true with our frequency encoding direction. So basically our frequency encoding direction is the time that we're sampling the signal. And if we have a very steep frequency encoding direction, do we get a smaller field of view or a larger field of view? Smaller field of view. Good. But the frequency portion of the matrix is determined by how many data points we collect during that sampling time. So if I said 128 by 128, we collect 128 sampling points. We take a snapshot of that signal 128 times to get a good true representation of that signal. So we just take, that's probably not the best color, 128 little dots across this signal to really get a good true representation of that signal. What's that issue? If we only take one
Aliasing.
It's aliasing in the frequency direction. That's the artifact. But we have to abide by what theorem? The Nyquist theorem. That's basically where we have to take 2 data points per cycle of that wave. Okay, so we always have to have a true representation of that signal. If we only took 1 data point in a cycle, we're going to get a straight line across that wave, and that won't be a true representation of that signal. So good. So remember those facts about K-space. The book likes to give the analogy of the chest of drawers that are filled with socks or different types of clothing. So the slice select gradient turns on first, so that determines which chest you're going to be filling. So if you have, say, a couple of dressers in your room, you're going to select maybe the dresser on the left to start filling. The phase encoding gradient will determine which drawer within that dresser to start filling. And then your frequency encoding gradient will basically have, you're filling that drawer with socks, which are the data points. So imagine if you had 128 socks or pairs of socks within that drawer, those are going to be your data points within that drawer that's within that dresser. Okay? So once you've filled all the drawers of that dresser, you have filled K-space. And once you've filled all your dressers within your room, you've completed the full sequence. So hopefully people don't have 128 pairs of socks, because I tend to lose 1 sock per load of laundry, so that's a lot of socks you're going to be losing. I don't know where they go, but it always happens. But the main thing to remember here, if you don't really kind of grasp that analogy, is slice select first, phase encoding second, frequency encoding last. So here are some options to fill K-space, and we'll review this a little bit later in the class. We have a rectangular field of view, and this is usually associated when we have very long and skinny anatomy, so like the L-spine, where it's a very basically tall structure, because you have to basically start at the T-spine, get all the way down to the sacrum, but you're not really concerned with the width of that structure. You don't need to get the belly or the posterior fat of the L-spine. So we actually apply what we call rectangular field of view. And that could be also true for like your humerus or your forearm, where it's a very long axis of the anatomy, but not a very wide axis of the anatomy. Anti-aliasing, this is where we're employing the phase oversampling. Fast spin echo are also called turbo spin echo. That's where we're filling multiple lines of K-space per TR period. So we have multiple echoes being filled per TR period. Keyhole imaging, this is more associated with MRA, where we're going to fill the center portion of K-space, and then we'll go back and fill the periphery because we're more concerned with the vessel compared to getting detail. And then we'll talk about some other ways that we can fill K-space a little bit later on. So that last step before we actually have our image is applying that fast Fourier transformation, which is a complicated mathematical algorithm. This occurs in the array processor. Like I said, it's the last step before image formation. This is where we're going to be converting data from signal amplitude to its frequency. So here, this is kind of what we've been dealing with so far when we're talking about, this looks like our free induction decay, right? So this is amplitude of signal intensity over time. So what it does is basically, if you have one waveform within a frequency, you're going to get basically one spike of amplitude, and that's going to be put on a frequency domain. So we have a time domain over here, now it's a frequency domain. So this will be associated with just one tissue. But if we have two waveforms contained within a frequency, you're going to get two spikes on your frequency domain. And most of the time, the two major spikes you're going to be dealing with in MR imaging are what two tissues? Fat and water. Those are going to give you your biggest spikes. And usually on a 1.5 Tesla magnet, they're positioned 220 hertz apart. So our fast Fourier transformer converts our signal from a time domain to a frequency domain. Now you have amplitude for each tissue, so it's able to calculate the grayscale associated with every pixel. So now it's going to be able to associate a color on the grayscale with that signal amplitude. So if we have high signal amplitude areas, so this is K-space on the left here. So if we have high signal amplitude, remember I said the middle of K-space is associated with signal and contrast. So all these bright areas are going to be associated with bright areas on the MR image. So this little area right here might be the ventricles on a T2 weighted image. This little area right here of signal or data point might be associated with this bright area over here. Okay? And then the periphery of K-space is going to give us our resolution. So if you have a very blurry image, you don't have very high resolution. Any questions there? I want you guys to take that first worksheet, take a minute, maybe pair up. Why don't you guys pair up back there? You three pair up, and then Jenny move over here, and then Lily and Rachel pair up. But take about 5 or 10 minutes and just start filling out the first three problems of that worksheet.
This one is about whole sequence diagram. This one was whole sequence.
All right, so to quickly review this worksheet that I gave the students in class, I'm going to bring this over. This is from my whole sequence chapter, but I have created images of all the different pulse sequences you'll have to learn later on. But here is a pulse sequence, spin echo pulse sequence drawn to scale. Make sure you label each line correctly. So the first line is going to be always your RF pulse. Second line, slice select gradient. Third line, phase encoding. Fourth line, frequency encoding. And your last line is going to be your MR signal. So right here you have your first RF pulse, which is a 90-degree excitation pulse. Anytime we have an RF pulse turn on, or we're going to be exciting or refocusing our spins, our slice select gradient has to always be turned on. So I saw you guys, a couple of people drawing these. Make sure these squares are right underneath your RF pulses. Because we want to only excite the hydrogen protons within that particular slice. And we want to ignore all the others. Our next gradient is going to be your phase encoding gradient. And so it can be drawn like this, but to more accurately depict it is the way I showed you guys earlier, where you're going to draw it more like this, hexagon. Because you are applying it with different polarity each time, and then a different gradient slope is applied, so more or less current is applied or sent through that gradient to get steep or shallow gradients. So you can put a positive up here, a negative down here, and put shallow slope closer to the central axis, steep slope further away from the central axis. So each TR period, so remember 90 to 90, we are selecting one of these. So only one of these phase encoding slopes gets selected per TR period in a traditional spin echo pulse sequence. And then the next TR, we select maybe a negative polarity. So just be mindful of that. Our third and final gradient that is turned on is our readout gradient. So you can label this as your readout gradient. And then if you split the readout gradient in half, you get your rephasing of the signal. So see how our signal starts to regrow because of this 180-degree refocusing pulse. That is going to rephase our signal, or basically cause it to regrow. So this is a good thing. This basically regrows our signal. So the first portion is going to be our rephase. Our second portion is going to be our dephase. So make sure to put that on there. And then we have two times we're associated with in a traditional spin echo pulse sequence. We have our TE, which is from when we turn off our 90-degree excitation pulse to peak signal. So see how this graph is drawn? It just basically, they said peak signal TE, but remember, it's the time frame from when you turn off the 90-degree to when that signal sampled at the peak amplitude. That's your TE. And then your TR is going to be from 90 to the subsequent 90. So on here it's not drawn because we don't have another 90-degree. But just imagine I copy and pasted this and put it over here. So if I did something like this. Oh, now I messed it up. So just imagine another 90 over here. That's your TR. Okay? All right, next question. What was the order?
RF slice select gradient.
Okay. Number 1, slice select. What's number 2?
Phase.
And number 3, frequency. All right, and then the last part of this worksheet is basically one of the last slides of our PowerPoint today. So just make sure you know all of the important facts about K-space. So this is a good review for your test this weekend. Okay? But I guarantee you, if you don't see much of like drawing pulse sequence on this test, you're still going to need to know that for Chapter 5 on pulse sequences, and you'll get a lot of questions on how the pulse sequence is arranged on your registry. So make sure you're able to draw these things out, because that really helps kind of bring it home. All right, so let's go to this PDF review document. And let's review this entire chapter here. So make sure to bring this up. Okay. All right, so our gradients These are used to spatially encode our signal in all three dimensions, because with MRI we know we are going to be dealing with three orthogonal planes. The timing of these gradients, first we have to do our slice selection. We're going to localize the slice, whether it's a coronal, sagittal, or transverse slice, and we're going to also decide how thick we want that slice. What decides the thickness of the slice? Transmit bandwidth. Good. And does that show up on our MR console? No. Just slice thickness. So as we change our slice thickness, that's actually going to be changing our transmit bandwidth. So good. And then our second and third steps are going to be encoding the signal along both axes. Our long is going to be associated with the frequency encoding gradient. And our short axis is going to be associated with the phase encoding gradient. Anytime we apply a gradient magnetic field, we're going to be altering our static magnetic field slightly. And we're going to be altering it in a very linear fashion, where we have a very predictable path, where one side of the magnet is going to be stronger and the other side of the magnet is going to be weaker. So here we have isocenter, and that's going to be associated with the best homogeneity, and we're going to get the best fast saturation at isocenter. But we use this linear slope to excite hydrogen protons at different points in the anatomy. So as we change the field strength in a linear fashion, our precessional frequency changes in a linear fashion too, very proportional. So you can see here, here's our equation. What's this equation again?
The
Lumbar.
Okay, so what's W0?
Precessional.
Equals, and what's the lambda stand for? Gyromagnetic ratio and field strength. So remember, the gyromagnetic ratio is a constant. That's never going to change for hydrogen. So it's always going to be 42.57. So imagine right at isocenter, we have 1 Tesla magnet field strength. So then our precessional frequency is going to be 42.57. But since our field strength has been altered due to this gradient, we have a stronger end and a weaker end. So here we have a stronger end, so we now have to multiply it by a slightly stronger Tesla, and it gives us a slightly higher precessional frequency. Okay? Why is that important? Why do we need to alter our precessional frequency? The RF pulse. It needs to match, through resonance, our RF pulse. So we can apply our RF to that exact precessional frequency. So if we alter it, we can basically hone in on one precessional frequency to, say, excite a slice that's closer to the brain compared to a slice that's in the abdomen. So good. Our 3 physical gradients. So you guys need to know the difference between physical and logical. So make sure to highlight this. Our physical gradients are going to be the ones we've talked about in the past, where our Z gradient is going to be head to foot, and that's going to give us our axial slices, because we're going 90 degrees from that gradient. So here are our axial slices. So Z gradient is blue. Axial slices, head to foot. Our X gradient are going to give us our sagittal slices. So here's our X gradient going right to left, sagittal, and then we go 90 degrees from that, so it gives us our sagittal slices through the body. And then our Y gradient is going to give us our coronal, A to P. So you can see here, A to P. And then you go 90 degrees from that, gives us our coronal slices. If we apply 2 gradients at the same time, it's going to give us an oblique slice. Because we know a patient's not going to be able to lay in the scanner completely, I guess, in a very predictable fashion where their head's going to be perfectly in the center, Their feet are going to be perfectly in the center. They might have to be laid on their side just because it's painful to maybe lay on their right hip. So they have to be sometimes put in an oblique fashion. The anatomy within our body is not always on a perfect right angle. So we always have to sometimes apply oblique slices a lot more often than you think. But to acquire an oblique slice, you have to apply two gradients at the same time. If we apply more current within these gradients, we're going to get a steeper slope. And if you get a steeper slope, you get a wider range in precessional frequencies. So if you get a wider range of precessional frequencies, you have a tendency to get thinner slices and to cover a larger area of anatomy sometimes. So a steeper slope, wider range of precessional frequencies.
And you said we get more slides?
Sometimes we'd be able to get more slices.
Thinner slices.
But you'll definitely get thinner slices, yeah. Steeper gradient slopes are usually always associated with thinner slices. Or better resolution. All right. So this is one thing we haven't really talked about. Sometimes on the registry they'll ask about logical gradients. And that's just usually a letter they assign to each task. So if the test asks which logical gradient is applied when slice selection is turned on in, they'll say, for a sagittal plane, all you have to really hone in on is the word slice selection. Slice selection is always denoted as Z. Which physical gradient is Z? Axial. That's physical gradient. This is logical. So you basically just have to memorize these. This is not associated with any type of coronal, sagittal, or axial slice. So if you see on the test, it just says, if the slice select gradient is applied, select the answer that says Z. Z gradient. Okay? So slice select is always denoted as Z. Frequency encoding is denoted as X. And phase encoding is denoted as Y. That's logical. Slice selection occurs by exciting hydrogen protons within a selected area, and that's usually determined by transmit bandwidth. How that is done is basically applying an RF excitation pulse that resonates at the same precessional frequency as that particular area on the patient. So they always like to give you the tuning fork example, where if you're trying to maybe acquire this slice right here, you have to apply an RF pulse at this precessional frequency, which is a little bit less than 42.57, to excite those hydrogen protons within that particular slice. And a slice thickness is determined by your transmit bandwidth. And usually you select a center frequency and then you create a range of frequencies that you want to excite. So a range that's a little bit more narrow is a narrow transmit bandwidth compared to a range that's a little bit more broad. That's a broad transmit bandwidth. That center frequency right here is also sometimes called your carrier frequency. So if your carrier frequency for this example is 41.20, you might have a transmit bandwidth that extends out just a little bit more. Oh, that's bad color. So that's your carrier frequency, but then your transmit bandwidth extends the amount of frequency that you're going to excite out a little bit more. So this would be considered almost like a thin slice. And then the blue here, if you select a broader transmit bandwidth, we select frequencies to excite that extend out a little bit further from your carrier frequency. Okay? So to select a thin slice, we usually have to have a steep slice select slope or a narrow transmit bandwidth. And just the opposite for a thick slice. We have to have a shallow slice select slope and or a broad transmit bandwidth. So I put down here 2 graphs to really hit that home. So this is slice thickness. This is your slice select slope right here. So in this top half right here, our transmit bandwidth stays the same. You can see here we have the same range of frequencies that we're going to excite. The only thing that's changed is our slice select slope. So we've got a steeper slope here, and that's associated with a thinner slice. But then we have a shallower slice select slope, starting to flatten out, and that's associated with a thicker slice. Down here, our slice select slope is the same. See how we have the same slope? But the only thing that's changed is our transmit bandwidth. So this is our transmit bandwidth. Is this a narrow or a broad transmit bandwidth? Good. So then see how that gives you a very thin slice. Okay? So there's really 2 ways to get thin slices. And they both deal with slice select slope or the transmit bandwidth. Frequency encoding gradient. This is a signal that's going to be located along the long axis. The readout gradient turns on when we're collecting the signal. Usually the signal regrows. It's rephased. So half of the sampling window, you basically sample at TE, and then that signal starts to dephase. The steepness of the slope determines the frequency field of view. We've talked about this before. If you have a very steep frequency gradient, it gives you a small field of view in the frequency direction. Okay? You always have to abide by the Nyquist theorem. And Nick kind of talked about it earlier, where you have to have at least 2 data points per cycle. So here we have many data points within this cycle. But if you really think about a full cycle, it has to basically go from the peak amplitude, go through center frequency to below the lowest point of our amplitude here. So we definitely have 2 data points for that one cycle. So this would be considered one cycle. We have 2 data points. So we're abiding by that Nyquist theorem. If we only had 1 data point per cycle, we would not get a true representation of our signal. Our sampling time is basically this rectangle that we've drawn on our frequency encoding gradient. The length of time that we're sampling the signal. That's called sampling time or acquisition window. That's the duration of the readout gradient. The sampling rate is how many of those data points we're collecting per our sampling time. So, and they usually do it per second. So it's the rate at which frequencies are sampled or digitized during the acquisition window per second. So if we have a higher sampling frequency, we're basically acquiring a snapshot of that signal very rapidly. So we're taking a look at our signal in those photographs very rapidly. We're taking more photographs during that sampling window. Our receiver bandwidth, this is the range of frequencies. So if you have your center axis here, if your receiver bandwidth is 32 kilohertz, we have 16 kilohertz above center frequency and 16 kilohertz below. We talked about K-space. This really talks about the important facts. I have 4 here, I have 5, but remember I added that 6th one, which is the data points create the matrix of K-space. Up here we have the pulse sequence diagram, and it shows you how K-space is filled. So as our slice select gradient is turned on, we are exciting one slice. So the entire rectangle is one slice. Then we turn on our phase encoding gradient. Say we apply a shallow gradient. Our shallow gradient is going to be associated with just one row of K-space. And then we turn on our frequency encoding gradient to collect the signal. So all this signal that's being rephased and then dephased is going to be put into that row, but all the little data points on that signal, all these little data points are going to give us our frequency encoding direction. So each TR period, you're going to be filling a different row of K-space, and that signal is going to be dropped into that row of K-space. K-space is not the image. It still needs to go through the fast Fourier transformer. Data is symmetrical. The center of K-space is going to be your signal and contrast. Your outer edge is going to be resolution. The time to fill K-space is going to be your scan time. TR times phase encoding times next. This is what your fast Fourier transformer does. We go from a time domain where our signal decays slowly to a frequency domain. So here we have one waveform, so we're going to be associated with one peak of that tissue signal. And then here I ended it with different ways that you can fill K-space. So review these where you take the test. So these are all the different ways that you can fill K-space. Okay. Any questions?
Are those going to be on the test?
A couple of them, yeah. Any questions? Take a break and we'll start at 10:20.